Hello everyone, this chapter will focus on technical principles of streaming.
After this course, we'll be able to know real-time stream processing, system architecture and key features of streaming, and also some basic CQL concepts. First, let's take a look at the introduction to streaming.
Streaming is a distributed real-time computing framework based on the open source Storm. In simple terms, it's a distributed framework for real-time processing of big data, like Apache Hadoop is a distributed framework for batch processing. Streaming makes it easy to reliably process unbounded streams of data, doing for real-time processing what Hadoop did for batch processing. It works on task parallelism principle wherein the same code is executed on multiple nodes with different input data. It's simple, can be used with any programming language, and it's a lot of fun to use. Streaming has the following features. It performs data refresh and end-to-end delivery response in seconds or minutes, depends upon the problem. It has very low latency, and when processing data with streaming, unlike Hadoop, it computes data before persisting to disk, which ensures low latency. Besides, streaming supports continuous query and return the results to the client in time. And it's unbelievably fast because it has enormous power of processing data. It can keep up the performance even under the increasing load by adding resources linearly, which means highly scalable. It can be applied to a wide variety of use cases like real-time analysis, online machine learning, continuous computation, ETL, and more. Let me make a few examples of open source Storm. Many companies are using Storm as an integral part of their system, like Twitter. Twitter is using Apache Storm for its range of publisher analytics products. Publisher analytics products process each and every tweet and clicks in the Twitter platform. Apache Storm is deeply integrated with Twitter infrastructure. There is another example. Navisite is using Storm for event log monitoring or auditing system. Every log generated in the system will go through the Storm. Storm will check the message against the configured set of regular expression, and if there is a match, then that particular message will be saved to the database. In Fusion Insight, streaming is a computing framework for real-time processing. Streaming does not have any state managing capabilities. It instead uses Zookeeper to manage its cluster state, such as message acknowledgements, processing status, and so on. This enables streaming to start right from where it left, even after the restart. Compared with Spark Streaming, while Spark Streaming works an unbounded string of data like streaming does, but Spark Streaming is actually a micro-batch processing tool. Spark Streaming is built on top of Spark, and it needs to represent the incoming flow of data within a stream as a batch in order to operate. So Spark Streaming won't be able to support the low latencies. In application scenarios, streaming is suitable for cases that strictly require low latency, usually milliseconds, while Spark Streaming is suitable for cases with less demanding of low latency, usually seconds. Before I introduce the architecture of streaming, let me show some basic concepts. Topology is the overall calculation, represented visually as a network of spouts and bolts. Think of a simple linear graph with some nodes connected by directed edges. Now imagine that each one of these nodes represents a single process or computation, and each edge represents the result of one computation being passed as input to the next computation. A streaming topology is a graph of computation where the nodes represent some individual computations, and the edges represent the data being passed between nodes. We then feed data into this graph of computation in order to achieve some goal. Nimbus is a master node of streaming cluster. All other nodes in the cluster are called as worker nodes. Master node is responsible for distributing data among all the worker nodes, assigning tasks to worker nodes, and monitoring failures. The nodes that follow instructions given by the Nimbus are called as supervisors. A supervisor has multiple worker processes and it governs worker processes to complete the tasks assigned by the Nimbus. A worker will execute tasks related to a specific topology. A worker will not run a task by itself. Instead, it creates executors and asks them to perform a particular task. A worker process will have multiple executors. Spout is the source of stream. Generally, streaming accepts input data from raw data sources like Twitter Streaming API, Apache Kafka QE, and so on. Otherwise, you can write spouts to read data from data sources. Both is a component to process input streams and produce output streams. Both can perform the operations of filtering, aggregation, joining, interacting with data sources, and databases. Each spout or boat executes as many tasks across the cluster. Each task corresponds to one thread of execution, and string groupings define how to send tuples from one set of tasks to another set of tasks. Tuple is the main data structure in streaming. It's a list of ordered elements. By default, a tuple supports all data types. Generally, it's modeled as a set of comma-separated values and passed to a streaming cluster. Stream is an unordered sequence of tuples. Zookeeper is a service used by a cluster to coordinate between themselves. Nimbus is stateless, so it depends on Zookeeper to monitor the working node status. Zookeeper helps the supervisor to interact with the Nimbus. It's responsible to maintain the state of Nimbus and supervisor. Then let's take a look at the architecture of streaming. First, client submits service topologies to Nimbus. Nimbus receives tasks submitted by the client, assigns them to supervisor, and monitors the status. Supervisor monitors and receives tasks assigned by Nimbus and starts worker processes that it manages. Worker processes run component processing logic. Each worker is a JVM process. An executor is the thread that runs specific service logic, and Zookeeper provides distributed collaboration services for service processes. Nimbus, supervisor, and worker register their information in Zookeeper. This enables Nimbus to detect the health status of all roles. Then let me explain some concepts in detail. A topology is a real-time application running on the streaming platform. It's a DAG composed of components. A topology can concurrently run on multiple machines. Each machine runs a part of the DAG. A topology is similar to a MapReduce job. The difference is that topology is a resident program. Once started, a topology cannot stop unless it's manually terminated. Spout is the message source of streaming. Generally, it reads data from an external data source and sends the data to a topology. For example, Spout can read messages from a Kafka queue and sends them as a stream, and both can receive multiple input streams. After some processing, some bots may send new streams. Complex string conversion operations, such as generating hot topics from Weibo messages, may involve multiple steps and thus require multiple bots. Both can run functions, filter tuples, aggregate and merge data, and access databases. String grouping specifies what streams can be accepted by bot as input streams and defines how to assign a stream to multiple tasks in a bot. A worker is a physical processing in running state in a topology. Each worker is a JVM process. Each topology may be executed by multiple workers. Each worker executes a logic subset of the topology. An executor is nothing but a single thread spawned by a worker process, and an executor runs one or more tasks, but only for a specific spout or a bot. A task performs actual data processing, so it's either a spout or a bot. A topology contains one or more workers that run concurrently on several servers. Therefore, a worker process is a topology subprocess, and a worker belongs only to a topology. A worker contains one or more executors, and each component has at least one executor. Therefore, an executor is a component execution subprocess, and an executor belongs only to a component. Tasks are specific processing logic objects. An executor thread can execute one or more tasks, but it only executes one task by default. Tasks are usually regarded as execution threads, but this is not true. The number of tasks indicates the maximum concurrency. The number of tasks in a component does not change, but the number of executors change. When the number of tasks is larger than that of executor, the number of executors indicates the actual concurrency. The concurrency of spout or bot is the number of tasks in spout and bot. In the preceding figure, there are two tasks in spout. This figure shows a topology, or we can say DAG, consisting of a spout and three bots, and the nodes on each part indicate tasks, and the lines between tasks indicate streams. But what about this one? What's a streaming group? We know by now that a stream is an unbounded sequence of tuples between a spout and bot or two bots. Part of defining a topology is specifying for each bot which streams it should receive as input. A string grouping defines how that stream should be partitioned among the bot's tasks. That is to say, a string grouping defines how the tuples are sent between instances of those spouts and bots. There are 8 built-in string groupings in streaming. For fields grouping, the stream is partitioned by the fields specified in the grouping. For example, if the stream is grouped by the user ID field, tuples with the same user ID will always go to the same task, but tuples with different user IDs may go to different tasks. For global grouping, the entire stream goes to a single one of the bot tasks. Specifically, it goes to the task with the lowest ID. For shuffle grouping, tuples are randomly distributed across the bot tasks in a way such that each bot is guaranteed to get an equal number of tuples. For local or shuffle grouping, if the target pod has one or more tasks in the same worker process, tuples will be shuffled to just those in-process tasks. Otherwise, this acts like a normal shuffle grouping. For all grouping, the stream is replicated across all the both tasks, using this grouping with care. For direct grouping, this is a special kind of grouping. A string grouped this way means that the producer of the tuple decides which task of the consumer will receive this tuple. Direct groupings can only be declared on streams that have been declared as direct streams. A bot can get the task IDs of its consumers by either using the provided topology context or by keeping track of the output of the emit method in output collector. For partial key grouping, the stream is partitioned by the fields specified in the grouping, like the fields grouping, but are load balanced between two downstream bots, which provides better utilization of resources when the incoming data is skewed. For non-grouping, well, this grouping specifies that you don't care about how the stream is grouped. Currently, non-groupings are equivalent to shuffle groupings. Eventually, though, streaming will push down bots with non-groupings to execute in the same thread as the bot or spout they subscribe from. Then let me introduce some key features of streaming. The Nimbus HA mechanism ensures continuous service processing even if one Nimbus is faulty, improving the cluster availability. It is implemented using the Zookeeper distributed lock. Leader election and active standby failover are based on the contention between the active nimbus and the standby nimbus. Besides, metadata is periodically synchronized between the active and standby nimbus nodes to prevent topology data loss and the service interruption after active standby switch is performed. Disaster recovery, which we've seen before, it's a capability that services are automatically migrated from faulty nodes to normal ones, preventing service interruptions. For example, in this figure, if node 2 fails, the tasks will automatically transfer to node 1 and node 3 without manual operations. Streaming provides three levels of data reliability. At most once, the processed data may be lost, but it cannot be processed repeatedly. This reliability level offers the highest throughput. At least once, data may be processed repeatedly to ensure reliable data transmission. If response is not received within the specified time, the spout resends the data for processing. This reliability level may slightly affect system performance. And exactly once, data is successfully transmitted without loss or redundancy processing. This reliability level offers the poorest performance. In actual application, selecting the reliability level is based on service requirements. For example, for the services requiring high data reliability, use the exactly once level to ensure that data is processed only once. For the services insensitive to data loss, use other levels to improve system performance. For the level at least once and exactly once, streaming has two kinds of processing mechanism, ACK and Trident. Let me explain the ACK mechanism in detail. A streaming topology has a set of special anchor tasks that track the DAG of tuples for every spout tuple. When an anchor sees that a DAG is complete, it sends a message to the spout task that created the spout tuple to act the message. You can set the number of anchor tasks for topology in the configuration. Streaming defaults topology anchors to one task per worker. The best way to understand streaming's reliability implementation is to look at the life cycle of tuples and tuple DAGs. When a tuple is created in a topology, whether in a spout or a bolt, it's given a random 64-bit ID. These IDs are used by hackers to check the tuple DAG for every spout tuple. Every tuple knows the IDs of all the spout tuples for which it exists in their tuple trees. When you emit a new tuple in a bolt, the spout tuple IDs from the tuple's anchors are copied into the new tuple. When a tuple is hacked, it sends a message to the appropriate hacker tasks with information about how the tuple tree changed. In particular, it tells the hacker, I am now completed within the tree for this spout tuple, and there are the new tuples in the tree that were anchored to me. As mentioned already, you can have an arbitrary number of hacker tasks in a topology. This leads to the following question. When the tuple is hacked in the topology, how does it know to which hacker task to send that information? Streaming uses mod hashing to map a spout tuple ID to an hacker task. Since every tuple carries with it the spout tuple IDs of all the trees they exist within, they know which hacker tasks to communicate with. If reliability isn't important to you, that is, you don't care about losing tuples in failure situations, then you can improve performance by not checking the tuple tree for spout tuples. Not checking a tuple tree reduces the number of messages transferred by half, since normally there is an ACK message for every tuple in the tuple tree. Additionally, it requires fewer IDs to be kept in each downstream tuple, reducing bandwidth usage. There are three ways to remove reliability. The first is to set config topology hackers to 0. In this case, streaming will call the hack method on the spout immediately after the spout emits a tuple. The tuple tree won't be checked. The second way is to remove reliability on a message by message basis. You can turn off checking for an individual spout tuple by omitting a message ID in the spout output collector emit method. Finally, if you don't care if a particular subset of the tuple downstream in the topology failed to be processed, you can emit them as unanchored tuples. Since they are not anchored to any spout tuples, they won't cause any spout tuples to fail if they are not hacked. Streaming provides a real-time distributed computing framework. It can obtain real-time messages from data sources such as Kafka, perform high throughput and low latency real-time computing on a real-time platform, and export results to message queues or implement data persistence to other components. Streaming is a computing platform and provides continuous query language in the service layer to facilitate service implementation. SQL is a SQL-like language used for real-time stream processing. Compared with SQL, SQL has introduced the concept of window, which allows data to be stored and processed in the memory. The SQL output is the computing results of data streams at a specific time. The user of SQL accelerates service development, enables tasks to be easily submitted to the streaming platform for real-time processing, facilitates output of results, and allows tasks to be terminated at the appropriate time. SQL has the following features. The SQL syntax is similar to the SQL syntax. Users who have basic knowledge of SQL can easily learn SQL and use SQL to develop services. In addition to basic expressions provided by SQL, SQL provides functions such as windows, filtering, and concurrency setting for stream processing. And CQL provides an extension interface to supporting increasingly complex service scenarios. Users can customize the input, output, serialization, and deserialization to meet specific service requirements. Besides, CQL provides detailed explanation of error codes, facilitating users to rectify faults. Here is the comparison of code between Storm and the Stream CQL. It's obvious that Stream CQL is much easier to use. And this is the architecture of Stream CQL. At the bottom is the computing engine, which usually refers to Storm or other stream processing engines. Stream and window here are built on stream processing engines and serve as the basis of all stream CQL functions. Above stream and window are a collection of functional algorithms such as join, split, and merge. At the topmost layer are open query interfaces such as SQL or IDE.
So this chapter briefly introduced streaming, like its definition, application scenarios, position infusion insight, and the system architecture and key features of streaming. Also introduced Stream CQL.
Okay, that's all for streaming. Thank you.